Hi, this is Math 1115. This is remote delivery for April 22nd, 2020. This is part 3 of 4, and in this lecture we cover section 6.6. The technique is we multiply each term in the equation, both sides, by the least common denominator. That eliminates all the fractions, and we can solve the resulting equation. There is a possibility of that introducing what we call extraneous roots, so we have to check the solution in the original equation. Let's do an example. Here we have an equation to solve, a lot of fractions. The least common denominator of the terms is 24, so I multiply all the way through by 24 each term. So 24 times this one, 24 times this one, and 24 times this one. 6 will go into 24 4 times, 8 will go into 24 3 times, and 12 will go into 24 2 times. So this is a linear equation for us to solve. We solve it, we get x is equal to minus 11 over 2. There's no problem here because the denominator is never 0. There are no extraneous roots. Here we have solving a literal equation. We want to solve for x. Again, we've got a bunch of denominators, so we're going to multiply all the way through by 2b squared, which is the least common denominator, each term by 2b squared. So 2b squared here, 2b squared here, 2b squared here, both sides. Here the 2's will cancel, here the b squareds will cancel, and here the 2b will cancel, and that gives us this expression. Now we want to solve for x, so we get all the terms involving x on the same side and things on the other. So we're going to subtract this from both sides, and we're going to add the 2 to both sides, and that gives us this. Now we have two terms here, and x is in both of them, so the only way to solve for this is to factor the x out. So we have x times b squared minus b. To solve this, we're going to divide all the way through by the coefficient of x, so the answer is this, 2 over b squared minus b. This equation comes up in optics, and we want to solve this for q. This is really f over 1, so the least common denominator across the whole thing is p plus q. So we multiply both sides all the way through by p plus q. When we do that here, we just get f times p plus q. Here we get this, and those will now cancel, and I just am left with pq. I'm solving for q, so I'm going to get every term involving the q on the same side and everything else on the other side. So I'm going to move this one to the other side, and I'm going to move this one over here. Now I have two terms involving q's, so I'm going to factor the q out. This is q times f minus p. Again, factoring is this. I'm going to divide both sides by the coefficient here. It is f minus p. All three of these things algebraically mean the same thing, and you don't have to worry about which one you use. This is an equation that's used in planetary motion where m is the mass of a large planet or heavenly body, I guess I will say. We want to solve for capital M, and we have a least common denominator of 2ar. So we're multiplying all the way through each term by 2ar. So we multiply by 2ar here, 2ar here, and 2ar here. Over here, the 2's will cancel. Over here, the r's will cancel. And over here, the 2a's will cancel, giving us this. Now we're going to get all the terms that have the capital M on the same side. So we're going to add this one to both sides, and we're going to be subtracting this from both sides, which gives us this. Now the capital M is in both terms, so we're going to factor it out again, and we get RG minus 2AG is the coefficient. We're going to divide both sides by that, and this is the solution, and it can be written different ways. Here's an example 5. The least common denominator here is going to be x times x plus 1, so I multiply all the way through by x times x plus 1. This term by that, this term by x times x plus 1, and this term by x times x plus 1. Now here the x and the x plus 1 are going to cancel, giving us minus 2. Here the x's will cancel, giving us x plus 1, and over here the x plus 1s will cancel, giving us 2x. This is a linear equation to solve, and we'll find out that x is minus 1. But x could not be minus 1 because that would have been a 0 in the denominator, and it's not going to check. X could not have been 0 either because that would have been a 0 in the denominator. So you see there is no solution here, and the x equal minus 1 is called an extraneous root. That's a fancy word that you won't be tested on in this class. Okay, here is a word problem because life is a word problem. An industrial firm uses a computer system to process data, and for an average day they do it in 20 minutes. To do it more rapidly, they're going to add a new component to the system, and one set of new components can process the data in 12 minutes without the present system. How long will it take the new system, a combination of the present system and the new components, to process the data? Well, you let x be the number of minutes it will take to process the data. Then x over 20 is the data processed by the present system. X over 12 is the part of the data processed by the new component. You see, this is work is equal to rate of doing work times the time. And together this is one complete job of processing. We're going to multiply all the way through by the least common denominator, which is 60. 60 times this, 60 times this, equals 60 times this. Here we get 3, here we get 5, and we solve this equation. We find out that it is 7.5 minutes. Distance is equal to rate times time, and this is another word problem. A bus averaging 80 kilometers per hour takes 1.5 hours longer to travel from Pittsburgh to Charlotte than a train that averages 96 kilometers per hour. How far apart are they? Well, distance equals rate times time, but that means distance over rate is time. So this is the time it takes for the bus. This is the time it takes for the train. And it takes the bus longer, and so you subtract the 2 and you get 1.5. Now the least common multiple is going to be, least common denominator is going to be 480. We multiply all the way through by 480 and solve, and we find out that D is 720. Life is a word problem, so I'm going to ask you to give this a go. Read the problem, press pause. Let's see how you did. May want to pause here too. That's it for part 3. See you in part 4.